Hello, in this video we're going to get into some of the details of how to compute the net signed area between the graph of a function and the interval it's defined over, which is related to the definite integral, using the limit definition. So we've got the net signed area definition on the screen here. I'm just going to quick go over to the animation we've seen in class before using Maple. All right, and I've got the right endpoint approximation here. I'm just going to click this forward, and we know that as we increase the number of subintervals we use and look at the sums of the areas of these rectangles, that gets closer and closer to the area under the curve. In this example, it's the area under this quadratic function between 0 and 5. We could also, and we will see in this partly in this video and in some of the next videos, examples where we're going to either use a left endpoint approximation or a right endpoint, which is the previous. Now we're looking at left endpoints. And again, as we increase the number of subintervals, the sums of the areas of the rectangles gets closer and closer to the actual area under the curve. Notice we're adding up the areas of these rectangles. The height of the rectangle is the constant function, which is given by the function value at the left endpoint. Could also do this with midpoints. All right, and they each have their uses. All right, and we're going to investigate each type here. So for the definition of net signed area, all right, we've got that limit. All right, it's limit as we add up, sum up we call this the Riemann sum inside of that. All right, we're taking the limit as we make the number of rectangles increase in more and more and more. This multiplication here, the function value times delta x, that's the area of the rectangle. So we're adding them together. The sigma notation means to add up, and then we're taking the limit as we use more and more and more. Notice in this definition, delta x is the width of each subinterval. So we're talking about what we refer to as a regular partition of the interval. All right, if we go back to the animation, each of these boxes had the same width, or each subinterval had the same width. That doesn't necessarily need to be the case. No, and also x sub k star is some point in the kth subinterval. Oftentimes we're going to use, again, right endpoints or left endpoints or midpoints. It doesn't have to be one of those, though. All right, related to this is what it means for a function to be integral and the definition of what we call the definite integral. The definite integral is this symbol here where we have the integral sign with the numbers a and b as what we call the lower and upper limits of integration. All right, we say the function's integrable if this limit exists. Now it's very similar to the one above, except the main difference is that this delta x sub k we're seeing in there is the width of the kth subinterval. So this allows the subintervals to vary in width, which is sometimes convenient for computation. We're saying this definite integral will be the limit as the number of subintervals will get larger and larger, but the maximum width of the subinterval is approaching 0, all right, for as n is going to increase as we're increasing the number of subintervals used. All right, and that's the more general definition of the definite integral. In practice, we're going to see in the next couple of recordings after this one, we're going to use a regular partition, and we're not going to have any difference between the width of the, say, first and the third subinterval and so on. Again, x sub k star is some point in the kth subinterval. What we call a partition is just breaking up your interval from a to b, all right, into a number of pieces. All right, you pick numbers where x sub 0 is the left endpoint a, x sub n is the right endpoint b, and you've got a bunch of other numbers in between. That's going to dictate n subintervals with those left and right endpoints. If all the subintervals have the same width, again, we refer to that as a regular partition. Most of the time, we're going to be working with regular partitions. All right. Okay, some more of the details. And again, the main focus we're going to get into in this recording is just understanding and quantifying what f of x sub k star is going to look like. In particular, what does that mean if we want it to be the left endpoint or the right endpoint or the midpoint? All right, so again, we're going to assume we're using a regular partition. We're going to break up this interval from a to b into n subintervals of equal width. All right, to do that, again, what we're going to think about doing here is taking this interval from A to B, we want to break it and divide that length up into n equal pieces. Well, the length of this interval is just take your bigger number minus your smaller number. This length is just going to be b minus a. All right, so we're going to take that as what we define to be delta x. So delta x is going to be the width of the subinterval, just the length of the interval divided by n. That's going to give you n subintervals as pictured now in this next figure here. All right, so we got our partition. I'm just going to kind of underline a couple of these things again. X sub 0 is equal a, x sub 1, x sub 2, x sub 3. In this figure, you're kind of leaving out, like, okay, we got dot, dot, dot kind of in the middle, and then eventually get to the end. The last one will be x sub n, which is equal to b. The previous one would be x sub n minus 1. All right, we'll get to those numbers on top in just a minute, but how do we quantify that, and how do we make this right here, how do we get a little more specificity for that dot, dot, dot business? And in particular, what is the kth subinterval? We don't see a kth subinterval in that picture right there. All right, so again, we want to quantify that expression x sub k star when we want to use either right endpoints or left endpoints or midpoints, and then we're going to plug that into the Riemann sum. Okay, and that, in the definition of the definite integral, which is the equivalent to the net signed area between the graph of the function and the interval a to b. All right, so I drew this number line picture here. And again, we want to know what is the kth interval, or what is the kth subinterval. So again, we've got x sub 0 is a. Well, we're going to go and add on delta x to get to the next point we've got there. All right, so that's telling us that x1 will just simply be a plus delta x. And then we're going to add another delta x on to get to x2. So we're just going to simply, okay, x2 is going to be a plus 2 steps of size delta x. Similar for x3, we're going to get another, add on another step of size delta x. So x sub 3 is going to be a plus delta x plus delta x plus delta x, which is just adding on 3 delta x's, or 3 steps of size delta x. Now, I'm going to label these subintervals here, just maybe using my black pen here. So this is going to be the first one, this is the second one, this is the third one. And notice for that third one, all right, the right endpoint's x sub 3, the left endpoint's x sub 2. For the second one, the right endpoint's x sub 2, the left endpoint's x sub 1. What's the kth one? Again, we got down, this is going to be our nth subinterval here. All right, which one of these is the kth? Is it in the middle here? That's what we want to kind of quantify, which wasn't in that other figure that we were looking at above. Well, again, the nth is x sub n, the right endpoint's x sub n. So it turns out this is going to be your kth subinterval, right? So this is going to be the kth subinterval here. All right, now how are we going to get to x sub k? All right, following the same pattern we've seen for x1 and x2 and x3, excuse me, the kth subinterval, or sorry, x sub k, which is going to be the right endpoint of the kth subinterval, is going to be a plus k times delta x. So we're going to take k steps of size delta x to get to the right endpoint of the kth subinterval. To get to the left endpoint, all right, so let's just make note here, this is your right endpoint. To get to the left endpoint, we're just going to go one less, x sub k minus 1, and that's going to simply be, forgive me for that, okay, it's just going to be one less, right? So it's going to be just replacing k by k minus 1. K minus 1 steps of size delta x. That's going to be your left endpoints. All right. Now, let's get to the midpoint. If I want to get the midpoint of any interval, in particular the kth subinterval, all right, let's kind of zoom in on that a little bit. I'm just going to bring this up a little bit. I want to get the midpoint of the kth subinterval. This is our kth subinterval from here to here. Well, from the left side to the right side is delta x. So with delta x, if I want to go halfway between, we're going to add on 1/2 of that width, so half delta x. All right, so if we want to get the midpoint of the kth subinterval, then what we're going to look to do is to take the left endpoint, x of k minus 1, and we're going to add on 1/2 times delta x to that. All right, now we already know what the left endpoint is. Left endpoint is a plus k minus 1. Clean that up a little bit. Times delta x. And then we're just going to add on 1/2 delta x to that. Now we can combine like terms here with these last two. All right, and we're going to then have that the midpoint will look like a plus, factoring out the delta x, we're going to get minus 1 plus 1/2 times delta x, which is then just going to give us a plus, and then if we do the arithmetic here, well, negative 1 plus 1/2 is negative 1/2, so it's going to be k minus 1/2 times delta x. All right, so let's gather these results together. All right, so let's come back and summarize these, which I've got written out down below. So again, what we're wanting to know is if we need to, we're not going to do this a lot, but we're going to do a few examples where we use the limit definition for the definite integral or the net signed area, and we need to express the left endpoint or the right endpoints and the midpoints in that Riemann sum. So we need to know what is that number, x sub k star, that we're plugging in. Well, if we're using right endpoints, it's just x sub k. And we just wrote down that that's equal to a plus k times delta x. If we're using left endpoints, then that special number, x sub k star, which is the point in the kth subinterval that we're going to plug into the function, it's just x sub k minus 1 from our partition. And that we can write out if we're using a regular partition of the interval, a to b into n subintervals of equal width. It'll be the left endpoint a plus k minus 1 times delta x. If we want to use midpoints, then this special number x sub k star will be, as we just showed above, a plus k minus 1/2 times delta x. All right, so that's going to be very useful for us. So we just want to keep those in mind when we do the next couple of recordings, in which we're going to look at some examples implementing the limit definition of the definite integral.